Hello, my name is Jesse Musa, and I am a computer science major at the University of Texas at Dallas. I'm currently in Nova, which is a research lab making a self-driving car. So this gave me the motivation to find what the best 3D object detection method is for self-driving cars. So we'll be comparing sparse fuse dense with GlenNet. We'll be comparing these using accuracy, implementability, and time complexity. So, what is 3D object detection? It is when a computer detects the size, position, and rotation of an object in three-dimensional space using sensors. These sensors can be anything from cameras. Well, for a self-driving car, these sensors would be cameras and LiDAR. So what is a LiDAR? A LiDAR uses lasers to make a point cloud, and a point cloud contains thousands of points about the objects around it. So onto the first method, which is sparse fuse dense. This is a depth completion approach, which means it combines 3D LiDAR point cloud data with 2D pixel data from the camera. Pixel data is then used to create a pseudo LiDAR, which is a projection of 2D pixels into 3D points. This is a multimodal approach as it uses multiple sources of input to make a prediction. Onto the next method, which is GlenNet. GlenNet is an object detection model that uses uncertainty to boost the model. This is because of the large ambiguity in the ground truth of labeled datasets. This can be because of small LiDAR errors, or human error in making the datasets. So GlenNet works by making multiple predictions for where it believes that the object bounded box could be. The variances of this bounded box is then computed to get a label uncertainty for a single object. The label uncertainty is then extended downstream to improve the performance of the actual object detection. So now onto their comparisons. So in the accuracy comparison, which is an extremely important metric because we have to be confident in the model that we are using in the real world. Sparse fuse dense outperformed GlenNet in almost every single category. The only category that GlenNet outperformed sparse fuse dense was at an extremely high distance, which in most cases is unnecessary. So for accuracy, sparse fuse dense is better. Next, onto time complexity. This is another extremely important metric because it is paramount that the car has to be able to react to an obstacle in real time. The car not being able to perceive an obstacle can cause an accident or lead to a fatality. Sparse fuse dense has an execution time of around 0.1 seconds, which will give it 10 object predictions per second. On the other hand, GlenNet has an execution time of 0.04 seconds, which will give it about 25 3D object predictions per second. This means that GlenNet can make 15 more predictions than sparse fuse dense in the span of 1 second. This is important because that means that GlenNet is better at reacting quickly to sudden changes in the environment. Lastly, onto implementability. Sparse fuse dense is a multimodal approach, which means we'll need both a high quality camera and a LiDAR. A 16-ring LiDAR will come out to around $16,000, and a high quality camera will come out to around $500, making the cost for a sparse fuse dense approach to be $16,500. And for a GlenNet, which is a single modal approach, it will only need a LiDAR, a 16-ring LiDAR, which will come out to around $16,000 for GlenNet. This means that for implementability, GlenNet and sparse fuse dense are largely the same. So now for the conclusion. GlenNet using this label uncertainty is extremely resource effective and is also extremely good at predicting objects at a very far distance. But I believe that sparse fuse dense still has the edge in all other categories. It has a higher prediction accuracy in almost every single scenario, except from large distances. And even though it has 10 predictions per second, this will be good enough for real world use. Thank you.